Alright, welcome to the third video in our limit trilogy, and today we're proving that the limit of the reciprocal is the reciprocal of the limit. In other words, given a single function, this time f, such that the limit as x goes to a of f of x is some number L, and we're offered the additional guarantee that L isn't 0, we're going to show that the limit as x goes to a of 1 over f of x is just 1 over the limit that we were given, which is why we needed the additional guarantee that it's not 0, because dividing by 0 is not nice. So to start off, we're going to state it in terms of the definition. For every epsilon greater than 0 that we can imagine, there has to exist a corresponding delta, which is also greater than 0, such that x being within delta of a guarantees that 1 over f of x is within epsilon of 1 over L. And just like in our last video, what we first want to do is we want to convert this expression into a form where we can actually tease out a term that has an f of x minus L inside of it, because the limit that we're given only really gives us guarantees about that, and we're going to try to use that to imply some additional guarantees. So we're going to start off by doing a little cross multiplication, which will give us an L minus f of x in the numerator over an L times f of x in the denominator. Now, recall that because we're doing everything inside an absolute value, it's okay for us to commute the terms on either side of the minus sign, and we're also going to split out our factors. So we're going to group the f of x minus L in absolute value over L into one term, and we're going to group the 1 over f of x that remains into another term, which is also inside its own absolute value. And what we want to do, again, like in the last video, is we want to first look at separate constraints on each of these terms, and then choose a delta that makes both of them satisfy their individual constraints so that the product satisfies our epsilon. And we're going to actually start with the blue term first. Now, because this is a 1 over f of x, and just like before, we want to avoid division by 0, we want to have some kind of guarantee that f of x is not going to be 0. And we know that we can do that because we know that there's a region around A that we can use to squeeze f of x arbitrarily close to L. And we're going to be a little bit relaxed with how large this region is. We're going to choose our epsilon 1 that we're just going to use to constrain the behavior of the blue bracketed term to be L over 2, or rather the absolute value of L over 2. And what we want to say using this epsilon 1 is we want to pick first a zone where f of x is more than halfway between 0 and L. And we know from the fact that the limit exists that there exists a delta 1 which is greater than 0 such that f of x minus L, again we're going to drop qualifying everything in absolute value, f of x minus L is going to be smaller than L over 2. And we know that such a delta exists, and what we really want to use this delta to say is that f of x is actually greater than, or rather the absolute value of f of x is greater than the absolute value of L over 2. Again, this is just another way of saying that f is past the halfway point between 0 and L. So how are we going to do that? Well, first we're going to start off with a tautological statement that L is equal to itself. And like in the last video, we're going to modify this by adding 0 inside the absolute value term, but we're going to split that 0 this time into a minus f of x and a plus f of x. From here, we're going to invoke our friend the triangle inequality once again into splitting this absolute value into the sum of two individual absolute values, and the triangle inequality tells us that this is going to be greater than or equal to what we started with. This is going to become L minus f of x in one term plus the absolute value of f of x by itself. Now, from this statement, we already know that f of x minus L is smaller than L over 2. So let's highlight this left term in green. We know up here that so long as, and this is something that we forgot to write, so long as x minus a is smaller than delta 1, we have that this guarantee is true. So x minus a being smaller than delta 1 implies then that this blue term, which is the exact same, is also smaller than L over 2 in absolute value. So once we propagate the inequality all the way through, we get that the whole term is smaller than or equal to, or rather just smaller than, the absolute value of L over 2 plus the absolute value of f of x. Now all we're going to do is subtract L over 2 from both sides of this inequality so that finally we get that f of x in absolute value is greater than the absolute value of L divided by 2. All right, and we're going to carry this one step further. Now we're going to take the reciprocal of both sides, and this will force us to invert this inequality to have it point the other way. So this, in turn, implies that 1 over f of x is smaller than 2 over the absolute value of L. All right. So armed with this guarantee, which is our real gem from this little side process that we were doing just now, we can now say that x being within delta 1 of a ultimately implies that f of x minus L over L times this 1 over f of x is smaller than f of x minus L over L times this 2 over the absolute value of L, where we've now extended this absolute value to encompass the 2, but that was a positive 2 anyways, so it doesn't really matter. Regrouping terms, we're going to now group things like this so that we have the f of x minus L by itself inside absolute value bounds, and we'll also have a 2 over L squared in absolute value. And remember that, or rather now we're going to want to say that this is smaller than epsilon. And we're going to have to prove that. So we'll write down prove. And how are we going to do that? Well, this is going to be the same as what we really need to show, rather, is we need to show that f of x minus L in absolute value is smaller than epsilon times L squared over 2 in absolute value. But this f of x minus L is something that our limit tells us we can constrain, and we know that there exists a delta 2 such that x being within delta 2 of a guarantees this exact constraint. So finally, we choose delta to be the minimum. As you can see, this is a very common sort of strategy when doing epsilon delta proofs. Identify multiple deltas and show that you can satisfy them all by choosing your final delta to be the minimum of all of them. Choosing delta to be the minimum of all of these ensures that x will be trapped inside a region that satisfies this, meaning that it satisfies this, but satisfying this ultimately tells us that our original expression, which we regrouped and rearranged just a little bit, minus L over L times this 1 over f of x, all of this is smaller than our desired epsilon, finally completing the proof. So now we've shown that limit of a sum is the sum of the limits. We've shown limits of products can be turned into products of limits, and we've now shown additionally that limits of reciprocals can become reciprocals of limits. And these are kind of the foundational building blocks that allow us to then talk about more complex things. For example, we can combine this law or this property of limits with the product of properties limits to reason about taking limits as x goes to a of, say, f of x over g of x by first considering the product of 1 over g of x by itself and reasoning about that using this, and then combining that with the product property of limits to multiply the 1 over g of x limit with the f of x limit. And we can do that some more in the future. But for now, this video is done.